Hello friends, a very good morning to all of you. Myself Shrikant Bhardwaj. Today we will be learning ideal cycles for the IC engine. So let's start. Ideal cycles for IC engines. Now, generally we are having three ideal cycles for the internal combustion or the IC engines. The first one is your Otto cycle, then diesel cycle, then 12 cycle. So first we will deal with Otto cycle. Now on this Otto cycle, SI engines are mixed. What are SI engines? Spark ignition engines. Okay. And the fuel that is used here is petrol or gasoline. And Otto cycle, it is the principle on the working of your SI engine. Remember this thing. SI engine, that is spark ignition engine. Now let us move with PV and the TS diagram for this Otto cycle. PV diagram, and here I will draw TS diagram. Okay. So here this is pressure axis, this is volume, temperature, and entropy. In the PV diagram, there are four processes are there. 1, 2, 3, and 4. 1 to 2 is known as isentropic compression. So here PV raised to the power gamma is equals to constant. 2 to 3 is constant volume heat addition. So here volume is constant. 3 to 4 isentropy expansion. PV raised to the power gamma is constant. And 4 to 1 constant volume heat rejection. Now since 1 to 2 is isentropic, straight line, 2 to 3 constant volume, so with a slope, because with the it is a constant volume heat addition, with this there will be rise in temperature as well as of the entropy. So this is 1, 2, 3, and 4. This is your heat addition, 2 to 3, and this is heat rejection. Now moving further towards efficiency. Before efficiency, let us deal with types of processes in the Otto cycle. So 1 to 2, it is a isentropic compression. Isentropic compression. 2 to 3 constant volume heat addition. 3 to 4 isentropic expansion, and 4 to 1 constant volume heat rejection. Now efficiency of the Otto cycle. So efficiency is equals to output upon input. What is the output here? Work obtained upon heat addition. So work done from the engine is heat addition minus heat rejection upon heat addition. And this will be 1 minus heat rejection upon heat addition. Okay. And 1 minus heat addition, rejection, they both are the constant volume processes. So MCV, heat rejection is from T4 minus T1 upon MCV, heat addition, T3 minus T2. Here MCV and MCV get cancelled out. M is mass and CV is specific heat at constant volume. So what we are having here, 1 minus T4 minus T1 upon T3 minus T2. Let this to be equation A. Now, moving further, since compression ratio is equals to V1 by V2 and 1 to 2 is isentropic compression, that's why T2 by T1 whole raised to the power 1 upon gamma minus 1, and this you can say equals to R. Equation number 1. Expansion ratio it is equals to V4 by V3. So it is T3 by T4 whole raised to the power 1 upon gamma minus 1. And since we all know from the PV diagram, you can see that V2 is equals to V3 and V4 is equals to V1. So using this, we can write here that V1 by V2, which is equals to R, is equals to T3 by T4 whole raised to the power 1 upon gamma minus 1. Okay. Now from 1 and 2 equations, we can write that T3 by T4 is equals to T2 by T1. T2 by T1. So it implies that T4 by T3 is equals to T1 by T2. T4 by T3 is equals to T1 by T2, and using algebra, T4 minus T1 upon T3 minus T2. Now putting this value from third equation into the A equation. See, from here you can see that it is equals to 1 minus efficiency of the Otto cycle is equals to 1 minus, here you can see it is here that efficiency of the Otto cycle is equals to 1 minus T4 minus T1 upon T3 minus T2. So putting this value, efficiency of Otto cycle is 1 minus T1 by T2. It is 1 minus T1 by T2, which is equals to 1 minus 1 upon T2 by T1, and it is equals to 1 minus 1 upon R raised to the power gamma minus 1, or 1 minus 1 upon R raised to the power gamma minus 1. So this is the efficiency of a Otto cycle. Okay, that is the SI engines which work on this cycle. Thank you. I hope so that you like this video. Thank you very much.